Yes.
Can everyone hear me?
Yep.
Okay, good. Let's get started, everyone. Welcome. I will pray for us, then we'll get started. Last day of new material, and we are going to finish up radiation today. I'll go ahead and pray. Father in heaven, we're grateful that we can pray as we begin our meeting today, our class. We ask you to bless us, that we can understand one another, that we can, despite this difference, that we can learn together. We are grateful for the opportunities we have. We're grateful that we can fast and pray. We're grateful that we have a prophet. We ask you to please bless us, that we'll stay healthy, and bless those who are sick, that they can get healthy. We pray that the world can quickly return to normal. We ask you to bless the students, especially as they're finishing up their semester. They can manage their time well, study, and understand everything they need to prepare for finals, and that they'll be able to share the knowledge they've learned this semester. We say these things in the name of Jesus Christ. Amen. Okay. So I'm going to review a little bit today about this assumption that we have of when can alpha equal epsilon. And then we're going to go into this last topic we have about when you have mutual irradiation. So up until this point, we've basically been doing energy balances on one body, one small body. And we might have really big surroundings, or the sun, or a big oven, or something like that, like your homework. But it's basically, we've been worried about one object. What we're going to do today is if you have kind of two objects of approximately the same size, there's not one big one or one small one. Now there could be a lot of surroundings around those, but now we've got two bodies, and they're going to be irradiating each other. And the situation gets a little more complex because each thing is emitting, each thing is absorbing, and each thing could be reflecting or transmitting. We won't deal with the transmission one. We'll assume they're always opaque, but we'll get to when things reflect and when things also emit. To do that, we first need to revisit a little of this Kirchhoff's law and this idea of gray bodies. So Kirchhoff's law states that you can assume that for your body, your substance that you're trying to do the energy balance on, that alpha is equal to epsilon. This is, if you look back at the derivation of Kirchhoff's law, you see that this is only strictly true when you have a small object in a very big enclosure and everything is at the same temperature. So that seems fairly restrictive, and it is. But there are cases where you can set alpha equal to epsilon, and I've summarized those here in this section 1.2. There's two sets of criteria, and something from each set has to be satisfied to assume alpha is equal to epsilon. And I've tried to note here, this is almost never true for solar irradiation. That's why in table 12.3, you see kind of this example here, that this alpha S is alpha of the sun, or solar radiation, I guess. I could put that. the absorptivity of these materials from solar radiation. This is still a property of the material. It's not a property of the sun. It's a property of the material in the range or in the wavelength range of the sun's emissions. This is the emissivity of the material. And you can see that in many cases, they're vastly different. Now, this black paint seems to be okay, but that's kind of because it's kind of like a black body. But you can see for most of these, they're vastly different. So saying that alpha is equal to epsilon is a very bad assumption. And just to drive home that point, here's the ratio of all those. About the only one that is true with that is if you approximate a black body, like when you have black paint. So with solar irradiation, you almost never can assume alpha is equal to epsilon. Does anyone still have a problem with that idea? Okay. Now, if you're not in solar irradiation, the best thing to do is still see if you have a table like this. If you had a table like this for whatever irradiation was coming in, if it was coming from the sky or something like that, then it would be best to use that. But we rarely have that information. We just haven't taken the time, no one's taken the time to experimentally measure it. So so practically speaking, if you don't have alpha, you're going to assume alpha is equal to epsilon. But that's only strictly true when you have these criteria met. So criteria set 1 is that either the irradiation hitting the surface is diffuse, that means it doesn't depend on direction, or the surface is diffuse. So either something, when it's coming in, either it's diffuse, it doesn't matter if it's coming in from this angle or this angle, or the surface itself doesn't care which angle. So basically, you got to have something with diffuse. It doesn't care about the direction it's coming, that theta direction. So if one of these are true, and then also one of these are true, where either the irradiation is coming from a black body, so like the sun is a black body, the sky is a black body, or a big oven, so to speak, a big object compared to the small object is a black body, or the surface itself of the object is gray, which means it's not dependent on lambda. So diffuse means not dependent on angle, and then gray means not dependent on lambda. And so if you have diffuse and gray, or diffuse and that the irradiation was coming from a black body, then you can set alpha equal to epsilon. That's often why you see in the assumptions of the answer keys, well, you probably haven't seen yet because they were just posted with the homework today. You'll often see that it's gray and diffuse. We assume the surface is gray and diffuse. And when you say that, when you say diffuse is criteria set 1 plus gray, criteria set 2, what you're essentially saying is alpha is equal to epsilon. Does that make sense? From a practical speaking, you're going to know on the exam whether you can set alpha equal to epsilon. If you're not given an alpha, then it's going to be equal to epsilon, unless it's solar irradiation. And in solar irradiation, you go back to table this 12.3. Or I'd give you a table on the final or something like that. Okay, questions about that?
Dr. Knotts, is there a best way to determine if a surface is diffuse, or how do we make that assumption?
That's a good question. If you have, you're going to almost always assume it's diffuse unless you have other information, is the take-home message from that. We often just don't have the information. Now, if you are in some highly specialized places, jobs, and you will need to deal with radiation much more. They may have more information, like on if you're dealing with silicon and it's the 111 surface rather than the 100 surface or something like that, then you're going to say you could probably get some sort of angle dependence. It's going to depend on the direction it's hitting. But usually in most cases, we're dealing with things that are pretty isotropic in that sense. There's lots of different crystal grains that are throughout the surface. Unless you've really gone to really high trouble to make it all like a 111 surface, then you're almost always going to assume it's diffuse. And gray, you're almost always going to assume it's gray unless it's solar irradiation or something that's coming from something very hot like that. And so my take-home message with that is, this is fairly introductory. You're almost always going to assume that in this class. In fact, I'm not going to give you something where you can't, because we don't deal with, it'd be lots of integrals and things like that, and we don't want to deal with it. Okay. So everything we talked about on this section 1, sorry, I dropped my stylus here, is applicable for whether we have a single body with lots of big stuff irradiating it, or what we're going to talk about now is if we have two smaller bodies. You know, if I had a ball here and a square here, and they were at two different temperatures, they're going to irradiate mutually. And so this is what we're going to talk about, this mutual irradiation. That's what we mean by that. And imagine you have these two surfaces, A1, A2. These are just squares in this case. They're at different temperatures, but A1 is a little bigger than A2, you can see. And I hope you can see that if this thing is irradiating out in all directions, not all of the irradiation that's from area 1 is going to hit area 2. Some of it's just going off somewhere else. And similarly for area 2, not all of it is going to hit area 1. So when you have two small objects that are close to each other, they're irradiating, but not everything they're irradiating is hitting the other object. And so we have to start talking about the fraction of irradiation that does hit the other option. And we define what's called the view factor, which is literally the fraction of energy leaving surface I that is being intercepted or is hitting surface J. Now, notice it's radiosity. You guys are like, man, I don't remember what you're talking about with radiosity. What is that? Remember, radiosity is just all of the things that is emitting from some body plus the thing that might be reflected from it. So there's two ways things can go out, right? They can be reflecting, or they can, and they're also emitting. And so don't worry too much about that right now. Just know that it's the emission plus the reflection. And so I can define the fraction, this F, this view factor, of how much irradiation is coming from one body and hitting the other. And there is a big, huge derivation in the book that says this is the integral you have to solve. That if I have some sort of differential volumes and I define my normals like this, just some random normals that are normal to these surfaces, I can define two angles and I can define a distance. And that is the integral that you have to solve to get that view factor. Now, I'm going to show you some integrals. I will never make you do one of these integrals, but I want to show you that the math is possible. And then I'm going to show you the table where they've already done the math. But I want you to get the idea, right, is that we're going to take some sort of differential volume. 1 second. We're going to take some differential volume here on area 1. We're going to take the differential volume here on area 2. We're going to define the distance between them, and we can define the normals. And so we can define the angles, and then this, and then we'll have to integrate over the entire domain of these two bodies. And that, this integral, when we do that, will be our view factor. And so there's this example in the book where I have a small thing, a flat surface, and then I have a big surface, a big disk above that surface. So I have a little small thing and a big disk above it. And you're like, well, that's kind of a weird type application, but I'm showing you this because the math works easy. And then also I'll show you the table in the book where they do all the other complex things. Now, I actually had an error in my notes. I uploaded a new version right before class. So you might have something else here, like some sort of little r or something, and little r's. If you've got that, just go download the new version right now. But again, I am never going to make you do this integral. But I just kind of want to show you. So we have to define some sort of differential volume on both of these things, and you can see the angles. And if we're going to integrate over that disk, right, we're actually integrating shells. So the area is 2 pi x. That's kind of the circumference, right? How far I am, here's x, how far I am from the center, times the thickness. So this is the thickness. And for, I guess I forgot an h there. There we go. And for a infinitesimally small little shell, that's what my area is going to be. You can see I got theta 1, theta 2. I can define, this is just Pythagorean theorem, that I can get from the vertical distance and the horizontal distance in the x, and then I can get an r, the distance between these two bodies. I can just use normal trig to say this is adjacent over hypotenuse, and the hypotenuse is r, so I sub that in here. And then I'm going to start subbing in this theta phi all the way up into this integral here, and I'm going to substitute in r's for l's. And you have to do this integral. It comes out, this double integral. And you can get everything in terms of just the big diameter and the distance between the two objects. And the big take-home message is you don't have to do this for yourself. In the book, let me bring the book up here. In table 13.1 and 13.2, here's 13.1. So you've got parallel plates with midlines connected by a perpendicular. Basically, they are straight up and down, right? They're parallel to each other, straight up and down. You can see it's got widths of these two plates, the distance between them, and this is how you calculate the view factors, some kind of complex algebra. They got that by solving the integral that we just kind of talked about. I can get two planes that are at some angle. That's the view factor, perpendicular with a common edge. I can do this three-side triangle. You can do the math. I don't know why you would ever necessarily need that, but some math student, some grad student was able to figure out that integral, and it turned out to be pretty easy. What about two circles of different radii? Now, I want you to be clear here. These little gray areas here, I can't really write on them. In fact, give me 1 second. Let me go back to here. I might have it in PDF form. These little gray circles are not part of the objects. That's just defining I and j. I don't know why they did it like that, but it's just two circles at different radii. So you've got a distance between the surfaces, you've got the radii. This is what the view factor between those two would be, from I to j. And then we've got a cylinder and a parallel rectangle, things like this. Again, these are not part of the objects. Those gray parts are not part of the objects. What was that question?
Do we assume that these are extending infinitely in the third direction?
So if it says, so two cylinders, yes. So these are going this way, which is a fairly common thing in two cylinders, infinite dimensions are big things in plants, right? Because you got all sorts of pipes that are running back and forth. One might be hot, one might be cold. So that's actually a pretty big deal right there. Or you've got a pipe with a floor, something like that, where I've got a lot of cylinders running. And so people have figured out all these view factors. There's also these where I've got two parallel rectangles, I got two parallel discs, I've got these common edges. You can see that these get pretty complex, but again, it's just algebra. I wouldn't give you something this complex on a final exam. In fact, I don't even do it on your homework because That's just a lot of algebra. But the bottom line is, I'm not going to make you do any of those integrals. You've got common geometries here in tables 13.1 and 13.2 to give you the view factors. Now, I want to talk a little bit about, before we go into some examples, I want to talk a little bit about what the nomenclature here. When it says F12 right here, that is the view factor from 1 going to 2. And that is not the same as 2 going to 1. And I hope you can kind of see that here. In fact, let me just draw. If I had a circle here and a big circle here, and I called this one 1 and this one 2, you can see that all the stuff coming from 1, there's going to be a lot more of that than coming from 2 that actually hits 1. So Fij is not always equal to Fji. If there's symmetry, then that's true. But Fij is not always equal to Fji. But there's lots of rules for view factors that you need to know, because you're going to have to use these rules to generate all the view factors you need for your system. So let's talk through these rules. There's not that hard a rule. The first one's the summation rule. What's it mean? It means, notice I doesn't change in this summation. And so what that means is F11 plus F12 plus F13 plus da-da-da-da-da all the way up to F1n equals 1. That's one of the rules you can use. So if you just have 2 objects, n is the number of objects. If you just have 2 objects, then it would be F11 plus F12 equals 1. Okay. The can't see rule. Anything planar, it can't see itself. And I kind of drew that out right here. So that means that like F11 equals 0 if I called this area 1. Anything planar can't see itself. And a corollary to this is, well, if Fij equals 0, if 2 things can't see themselves. So if I had a circle right here and then a wall and a circle right here, then 1 to 2 would be 0, right? If I put something physically between them, it would be 0. Now, I want to also show you, this is planar or convex. So if I have a cylinder, and I'm talking about the surface of that cylinder, it can't see itself either. And if I call this object 1, F11 would be 0 in this case also, because all of the radiation is going out radially from that, and it doesn't see itself. So if it's planar or convex, then you know that it can't see itself. And then the last very useful one for view factors, and again, I'm not proving any of this because it's a lot of math. I don't want to prove it. And I don't find it particularly useful. I can accept these simple algebraic relationships. If you want to prove it, I think it's in the book, and you can go back. That's what the math people did. But this is reciprocity. Let's say I had 2 bodies. This is A1 F12 is equal to A2 F21. What this allows me to do is I usually know the areas. That means if I know F12, then I can get F21 from A1 F12 over F2 or area 2.
Dr. Nuts, does that equation always work when there aren't just 2 surfaces?
Yes, and so if I had like area 3, 5, it would be area 3 F3, 5 is area 5 F5, 3.
Does that assume that they're diffuse?
Oh, that's a good question. So all of this stuff, I think I probably forgot to mention this. All of this stuff that we're talking about assumes diffuse and when we get to the equations later, they're at least gray. So they can be black bodies also, because black bodies are by definition diffuse and gray. But so black bodies or gray bodies, all diffuse. And that's all I'll ever give you in this class. The nice thing about this reciprocity rule that I kind of have right here is you only ever need to know half, so to speak, of all the possible view factors, because you can always get the other half by reciprocity. You kind of see me sub that in there. There's one other rule that you can use, this additive nature of view factors. So if I split up this object into two right here, I have an area 1, area 2, and then I have area 3 is kind of at a different angle there. I can individually get area 1 with area 3 and area 2 with area 3, or by the opposite way, the area 3 to area 1, 2 goes like this. So you can add them together. You can also subtract them. And so if I wanted this object, I could calculate assuming area 2 was there, and then assuming area 3 was gone, and I could do that subtraction. So you can add them and subtract them. So let's do a couple examples here so you can see what I'm talking about. So I have a long duct, a long hemispherical duct right here. Area 1 is the flat part, area 2 is the hemisphere. I know by, let's start right here. I know there's a lot of writing here. I just kind of wrote out the summation rule first. F11 plus F12 equals 1. F11 is 0 because it's planar. And so that means I can kind of immediately write F12 is equal to 1. You can kind of see that, right? Everything that leaves area 1, because it doesn't hit itself, has got to be intercepted by area 2. But notice that backwards, area 2 does not all hit area 1, because some of that radiation is going to hit itself, but some of it will hit area 1. But I can find that view factor out by the reciprocity rule. This would be A2 F21 equals A1 F12. I would divide over, and that's what I did here already. Let me just get rid of that. The area of the flat part, area 1, would be the radius, 2 times the radius, so that's the width, times the length. And then I have area 1, 2, or area 2 would be half of what a circle would be. So there would be 2 pi RL here, but because it's hemispheres, it's only half. And so this 1 is F12 that we got right here. And all that simplifies out to be 2 over pi. And so only about 64% of the radiation coming from area 2 hits area 1. The rest hits itself. Here's a hemisphere in a disk. And notice that this disk is smaller than the hemisphere. So I've got kind of 3 areas here. I've got the area 1 for the disk. This might be if you had an ice rink. In fact, like up in Kearns, they have the Olympic Oval where they have an ice rink here, and then they have a track on the outside where you have the speed skaters. So you have the hockey rink in the middle, and then you have speed skaters on the outside. But I have 3 different areas covering this big dome. So how do I figure that out? This is often something you just kind of have to say, well, I know that F11 has to equal 0 and F33 have to equal 0. So I'm going to kind of start there. I'm going to start with some surfaces here. F11 plus F12 plus F13, that's the summation rule. I know 1, 1 has to be 0, and I know 1, 3 has to be 0 because they're all on the same plane. So I can immediately write kind of F12 equal 1. I'm going to do summation for area 3, 3, 1. Those are coplanar, so those are 0. 3, 3 is planar, so it's got to be 0. So F32 is equal to 1. Now I got to start just seeing what other rules I have. One of them's reciprocity. I always have that. So remember, A2 F23 equals A3 F21. And the area 3 you see here, well, actually, all of this is area 3. So I take the total diameter minus that little small diameter, and then I divide by that other area, and I can get my other view factor, 2, 3. And I do something similar for 2, 1. And then I can use summation rule one more time to get the last one. And so it's kind of a little game. You just kind of go with what you got. And you're going to get a little practice on this on your homework to get these view factors. But you've got table 3-1, table 3-2 to kind of get you started. You also know anything coplanar or flat or convex, that one's going to equal 0. Let's do this one more, this triangle, these inclined planes. Now there's actually a thing in the chart for this, but I'm not going to use it. I'm going to show you how you can get a lot of this from symmetry. So I write the summation out, and I know that F11 has to equal 0 because it's planar. I also can write kind of an imaginary surface. And I know that this is kind of an isosceles triangle here because I made it that way intentionally. And that means 1, 2, and 1, 3 have to be equal. And so I can sub one of those into here and find out that they have to equal 1/2. 1 to 2 and 1 to 3. And you can kind of get that from symmetry. Half the stuff coming from 1 would have to hit 2. Half the stuff coming from 1 would have to equal 3. And then I can use reciprocity to get the last one. Okay, now that we've got view factors, we've got to talk about how to solve out when we have 2 or more bodies close together. And there is a lot of algebra in here, but I'm going to break it down to the simplest things. All it is doing energy balances on all of the reflection and all the radiation that you can get. And the book writes this as the net rate at which radiation leaves the surface. That means it's positive if it leaves, all the book, and which is a little different from what we do. Positive if leaves surface. So don't forget that. All of the equations you see. We're going to sub in, we're only doing opaque, so we're going to say the transmission is 0. And that means that the reflection is equal to 1 minus the absorption. We're going to start summing in a bunch of stuff. Go ahead.
So with the Q being positive there, does that mix with the other Q formulas we have if we were to combine this radiation net rate with like heat rates and stuff?
You're going to have to draw out your other equations. So like if you have convection, you're going to want to make sure that you're always saying it's positive going out. Now, that's going to be a tricky thing if you have to do like an unsteady state thing, but I don't give you one of those with this mutual irradiation. But in real life, if you're doing it, you're going to have to stick a negative sign on your unsteady state side. And so the answer to that question is you have to take care of it with your signs on everything has to be consistent. It all has to be defined as going out as positive, and then that would be taken into account on the unsteady state term with a negative sign, which I'll never do in this class, but if you had to, you could do it.
Okay, thanks.
Okay, what you're gonna get in the end, I don't want to do this derivation because I want to give you lots of examples here, and I got lots of examples. You're gonna find that the net rate of heat leaving body I looks like this. And you know how to get this. This is area. This is the view factor. These are the radiosities. And you're like, how do I get the radiosities? What you're going to do is you're going to solve a system of equation to get those. And I'll show you that in a second. And then I also can write this key equation. And you're like, I don't know where that comes from. Just accept it right now. And if you want to, go in the book and you can see the derivation, but it's there. Where you can see that the right-hand sides of both these equations are the same. The left-hand side has this EB is sigma Ti to the 4th. And this is the emissivity. And then this Ji is the same as this Ji, this one. Here's what you're going to do. Whenever you have multiple objects, you're going to write a system of equations. You can write one of these for each object. And the unknown is going to be ji's. And so you're going to have 3 unknowns, J1, J2, J3 if you had 3 bodies. You would have to know the temperatures, of course, or you wouldn't be able to solve that out. And I kind of summarize that here. What are you going to do if you're trying to get the net radiative heat transfer from each object? I first calculate the view factors. I then write those 3 equations and solve for the ji's. And then once I have those ji's, I can sub them in here to get q's. And that's what it says here. If they're black bodies rather than gray bodies, that just means that epsilon is equal to 1, and it gets a little simpler because I can just go right here and sub in e's for this. There's no reflection. So let's go through both of these examples. Skip down here. I want to do example number 2. So skip all the way to number 2 because that's the hardest one. I want to make sure I get through this one. Gray body radiation example. And once you kind of do a couple of these, I wouldn't say it's fun, but it's not hard. It's kind of recipe following. I've got a furnace, and I don't know how I would make this furnace, but this is just an example that's probably as most complex as you could get. But it's a cylindrical surface, and each surface is at a different temperature. So one end of the furnace is at 400, one end is at 500, and then the cylindrical part is at 800. So the most general you could possibly kind of get with 3 bodies. And all of them are at finite temperatures, and so all of them are hitting each other, and all of them are also reflecting some of the stuff that's hitting them. I also did it most general and made 3 different emissivities. And the question is, what is the net radiative heat transfer from each surface? What is Q1, Q2, Q3? And remember, this is from surface. So that means it's positive if it is going out from the surface. So I'm going to follow this little recipe. I'm going to calculate view factors. I'm going to write the 3 equations, 3 unknowns to get j's, and then I'm going to use those j's to get q's. And I've been very deliberate when I'm doing these examples to tell you what equations are which. So I've replicated them here. This is ultimately what I'm looking for, Q. That's equation 13.22. But to get that, I need radiosities, and I say that out. Thus, the radiosities of each surface are needed. Those are found by writing 3 of these equations. I'm going to solve these equations to get the ji's, and then I'm going to put the ji's into equation 13.22. Notice that this equation right here has an EB in it. And so the first thing I'm going to do is calculate EB. Well, actually, I'm going to first calculate view factors. And so I've summarized that again. Calculate FIs, calculate J's, calculate Q's. And there's a little M that's missing right here. So the first thing is, I've got to get all the view factors for this sort of looking thing. I know the first thing, well, I don't know if you know this, but you've got to have somewhere to start. I know that area 1,1, so I know F11 will equal 0 because it's a plane, and F22 has to equal 0 because it's a plane. But I also know that 1 and 2 are parallel disks, and that is in table 13.2. Let me go there real quick. Parallel disks, coaxial parallel disks. And so I need to know the distance L, and I need to know the radii of each disk. And then I'm going to calculate this big Ri, big Rj, calculate S, and then calculate Fij. And so that's what I do first. I calculate big R, big R1, big R2, again from table 13.2, and S. Just pull, there's no rhyme or reason to this. I just pull it out of the recipe. And then I get F12. So now I have F12. And I can start using my rules from there to get other things. So if I know F12, sorry, is it F12 or F2? Yeah, F12. Yeah, so I know F12, and I know by reciprocity that I can get F21. And also remember that area 1 is equal to area 2 in this cylinder. So F12 has to equal F21. That's what I do next. I can then write the summation rule to get F13 because I have F11 is equal to 0. F12 I just calculated above, so now I can get F13. I can do the similar thing for area 2 to get F23. Right, summation rule, it's planar, so F22 equals 0. F23 just equals this. And the final two view factors I get from reciprocity then. I can write two reciprocity relationships to get F31 and F32. And so again, this is just kind of a, you know, I've got these rules, I've got the table, and anything I give you, you'll be able to get the view factors based on these rules and these tables. So that's step 1, get all the view factors. Step 2, I need to write one of these equations for area 1, area 2, area 3. Notice that EB is found in each one of those equations, and that's just the as if it was black body type radiation. You know how to do that, sigma times t to the 4th. And so I just do sigma times t to the 4th. I calculate those out first. Sigma 1 or T1, T2, T3 to the 4th. And now I'm going to write, in fact, I think I wrote them again, 3 equations, 3 unknowns. I'm going to subtract the left-hand side from the right-hand side. This side is the summation of the J's. And remember, I don't know J's. Those are my guesses. I've got to solve for those. But I know areas, I know Fij's, I know EB, and I know epsilons. All those have to be given in these. I'm going to solve 3 equations, 3 unknowns out. This is just to check the function to make sure I didn't have any errors in it. Well, at least that it evaluated out. And then I use fsolve. I do 3 guesses. And it comes out to be these values here. So that's step 2. Step 1 was get view factors. Step 2 is solve for the radiosities. And step 3 is use those radiosities in this equation to get Q. And so here's those 2 equations. This is 1, 2 and 1, 3 for that equation. This is 2, 1 and 2, 3 and so on and so forth. And then you can get your solutions here. And let's just double check or double say again, I guess, triple say it. If positive means out, so negative means in. And so surface 1 has 538 watts into the surface. Surface 2 has 600 watts into the surface. And surface 3 is sending out 1,000 watts, well, 1141. And so that's 3 equations, 3 unknowns. That's a 3-body solution. Let's do another example. 2 equations, or 2 surfaces. This one is very common. It's an enclosure. I put radiation shields around pipes. I have a pipe. I put some sort of reflective material around it to stop the radiation or reduce the radiation losses from it. So if I have a steam pipe. And so my pipe is 100 millimeter outside diameter. And this shield is placed 10 millimeters away from it. And it's some sort of reflective material. And you can kind of tell that because it has this low emissivity. I want it to have a low emissivity. I'm trying to reduce radiation losses. So the pipe will kind of have a high emissivity and the shield will have a low emissivity. The pipe's going to be hot, 120 degrees C. Let's say the other one's 35 degrees C. How much Q am I losing per length of this pipe from radiation? I'm going to follow the same thing. Remember, everything is, there's emission and there's reflection. So I have to solve for the radiosities. The first thing, and so I just replicate this again, right? This is the key equation. I want Q, I need radiosities. To get radiosities, I'm going to write 2 of these equations and solve for the 2 unknowns, the radiosities. And so the first thing I'm going to do is calculate the Fij's, then calculate J's, and then calculate Q's. And again, I've tried to remind you of this too. They're always gray and diffuse. So view factors. I know that the inside pipe, which I'm calling 1, or the inside cylinder, doesn't see itself because it's convex. That means that F11 has to equal 0. And that means F12 has to equal 1. And you can see that from just looking at the picture, or you could see it from the summation rule. F11 plus F12 has to equal 1. This goes to 0. So F12 equals 1. I can then use reciprocity to get F21. Remember the outside one, some of it's going to be hitting itself on the other side of the pipe, and some of it's going to be hitting area 1. And it comes out to be this. Most of it's hitting the other pipe at 83%. I already kind of said F12 equals 0, F11 equals 0, and then I use the last summation to get F22. So now I've got all the view factors. That's step 1. Step 2 is I've got to write this equation twice because I have 2 objects I'm care about. And then I'm going to solve for the radiosities. So I need the black body emission. I calculate those here. That's just sigma T1 to the 4th. And then the summation part is over here. So that's the right-hand side of that equation. And here's the left-hand side of that equation. Again, this is my function I'm giving to fsolve. I got to solve for 2 unknowns in this case. Again, I always kind of check my functions to make sure they're returning the objective function correctly. Then I got my guesses. I give it to fsolve, and it solves out my radiosities. So that's step 2. Step 3, I use my radiosities to get Q. Here's the equation written out again. Once I have my radiosities, I can calculate Q. And in this case, it's only 1 term because there's only 2 objects, and object 1 doesn't see itself. And so this is how much heat loss you're now getting from radiation, which would be much less than if I didn't have that shield on. So I've given you a 3-body example. I've given you 2-body examples, both with gray surfaces. What about a black body? What about, oh, it's at the top, sorry. You're gonna say, if these are black bodies, then something gets a little tricky because I can't write radiosities. In fact, let's go right here. The reason black bodies become problematic is look at this equation right here. What's the radiosity for a black body? It is EBI, because there's no reflection. That's the only difference between them. So this gives you a 0. It doesn't mean anything. And so what you do, though, to get Q is you can just skip right to this top equation and replace your J's with EBIs. Come on, erase there. We're just going to skip right here and replace the J's with EBIs. And so that's the last example. Black body radiation. I've got an ice rink. It's got a big dome over it. And the dome is kind of bigger than the ice rink. I give you the dimensions there. And so you can probably see by now that F11 is going to equal 0. And then I can get F12 from F11 plus F12 is equal to 1. And so again, here's my key equations. This is what I want. But because it's a black body, and remember J is equal to E black body plus what's reflected, the reflection part, this is going to 0 because it's a black body. And so I replace this with just the epsilon from the E emission from black body. And so these become pretty easy. Black body is much easier. I don't have to solve 3 equations, 3 unknowns. I just got to get the view factors, sub in Stefan-Boltzmann law, and this is now my equation. I already showed you how to get F12, and it comes out to be 36.943. So here's the things that you want to make sure you get. It's just kind of a recipe I've given you, that if you've got 2 small objects, that's the harder thing to figure out. If you've kind of got objects of the same size, I've got to take into account all the reflection and all the emission they're giving each other. And I do that using this method because they can reflect and they can also emit. So I first have to get the view factors, solve for the radiosities, and then use the radiosities to get Q. Okay, questions? So your first problem on homework is just kind of practicing getting view factors, using the summation rule, using the reciprocity rule, and using the planar rule, convex or planar rule. And then your next ones are going to be just practicing this. Get the F's, solve the system equation to get J's, solve the, use the J's to get Q's. I actually think this homework, if you kind of remember that step, it's going to be a little easier than the last one. These mutual bodies that are irradiating, it seems complex, and it is kind of complex, but the math isn't super complex. You just kind of follow the recipe. Okay. Well, we're about time. Next time, we're going to review. We're going to talk some qualitative stuff about radiation. I am going to send out a lot of info about the final exam. I don't want to talk a whole lot about the final exam on Wednesday because I want to spend that time reviewing. So make sure you read everything I send out so there's no questions. That'll make it so that you can, we can spend the time reviewing rather than asking questions the whole time. Okay, any final questions before we go?
We get an update on exam 2?
Man, that's a good question.
Yes, please.
I have asked the TA that's finishing those up. I said the students are going to get mad at me, and it's all your fault. And so she has not gotten back to me.
I saw N95 masks at work today.
I didn't hear that, but I will let you know as soon as I know. And I said, we got to have those back very soon. I would have one of the other TAs do it, but it's half done and I want to make sure it's all consistent. I hope you guys just all get A's on that. That'll just make everything easy, right? Yeah, I emailed the TA. I emailed the TA very early this morning and said, "What's up? I want to have this answer before I go to class today," and I did not get the answer.
Dr. Knotts?
Yeah.
Is it set in stone that the final will be at a specific time rather than throughout the week?
Well, it's definitely not going to be throughout the week.
Like whenever you want?
So the university, the info I got from the university, I don't know what your other teachers are doing, is they really want it to be during the normal time. And I think it's advantageous to do that because that way you can ask me questions if you have a question about what's on the final exam. But I will probably make 2 different times available.
Okay.
And so that's just kind of going with the university. The university wants it to be kind of like a normal final exam type thing.
Are we going to be using like Proctorio, or is that going to be all in the email?
I am not going to use Proctorio. I'm just going to, it's going to be on Learning Suite, and
You're going to be Zoom call with us all?
I didn't hear that last question.
Are you just going to be on a Zoom call with us all then?
Yeah, I'll be on a Zoom. I'll be on a Zoom call with you during the 3-hour block. That it takes, just like I would if I was giving it to you in class.
Perfect, thank you.
It's going to be advantageous to have me there, so that if you have a question, you can do a little chat, a personal chat with me, and I can say, I'll tell you this, or I'll tell the whole class, or stuff like that.
Dr. Knox, can we have a, oh, never mind. She can go first.
Thanks. Dr. Knotts, I noticed that the competency quizzes are due on Thursday. Would
Yeah,
you be okay with extending that deadline, or is Thursday a hard stop?
Well, I did extend it to Thursday. It was tomorrow. I don't know why I set it for tomorrow, but usually, here's the thing. Technically, I'm not, the university gets mad if I have anything due after reading day. So that's why I set it to the latest possible time before finals start. That's why they get mad if I have stuff due during finals week. But I've got time on Thursday during your reading day to help you through your final stuff, to make sure we get all those done.
Do it for the boys, Dr. Knotts.
Hey man, tell the university. It's all the university rules. You shouldn't have that many more to do, right? It should just be shell and tube.
How do we tell the university? Where do we send those emails?
Hey, I don't know. Where do you send the university anything? Here's the thing. You probably send it to the academic vice president's office. And I can tell you though that it's probably not high on his priority list. I think they actually
congregate there. We might get some action.
I think they actually have that rule more for your benefit so that the instructor doesn't load up, say, oh, I'm going to give 10 more assignments and they can do them all over finals week and stuff like that.
Well, I would just say don't brief the professors if the students ask for it. That's all I'm saying.
Are there any final reviews by the TAs?
I don't know. I'll send an email to them and see if they want to do some. I don't know if Tim's on right now or if Jansen's on. But I'll have them see if they want to do a final exam reviews.
Okay.
Hey, Dr. Knotts.
Yeah.
Could we do a private Zoom meeting after this once we're done so I can ask a question about the competency exams?
I've got one that's scheduled here. Send me an email and I'll see if I can schedule something.
Okay.
Hey, Dr. Knotts.
Yeah.
Will you be having regular office hours during finals week, I guess before the final?
So at 11 o'clock every day?
Yeah.
Yep.
Okay.
Will you be having office hours every day this week again, or at least until reading day?
So I have office hours. I'll have office hours at 11 o'clock all the way until next Thursday when the final happens.
Is the project computational task, do we turn that in as a group or individually?
Everything can be done as a group.
Thanks.
You're welcome. Okay. I've got to run to another Zoom meeting here. If you need me to talk to me, send me an email and we can set something up too. Okay. See you guys on Wednesday.
Thanks, Dr. Knotts.
You're welcome.